Hello, and welcome to what I think is the last talk of this conference. Hats off to you. You're either very interested in this topic or are curious about some aspects of it, and I hope to not disappoint you. The focus of my talk is controller design and some immediate activities around it. The larger topic of controller design itself is much bigger in scope. So we typically start with some requirements, and then we have to get the model to base the control design off. So the model may already be available to you, which is not typically the case, or you can use some system identification methods, or get it from first principles, or using drag and drop. For the latter two, we have very good capabilities. And then from modeling, we typically move on to analysis, and we have a whole suite of analysis tools. And then based on that, we go on to the controller design. And all this process is iterative. So when you do your analysis, you may feel like you have to go back and tweak the model a little bit, or when you do your controller design, you may feel that you may have to go back and tweak things upstream. And then based on the controller design, we do the simulation and post analysis, and then go to implementation and finally verification. So the whole process can be iterative. And over the years, we've been actually filling in various gaps in the workflow. And I would encourage you to look at this link to see all our capabilities in this area. So the focus of my talk is primarily in control design and the analysis after that. And control design itself is not just computing some numbers or an expression of the control law. So once we compute it, uh, to get a good workflow, we also have to put it back together with the system and then see how our controller performed. And that's where all these tools come in to actually ease in that process. Let's start with, so I'm going to start with an example. So here I have an example of a control design. So here I have a chemical system with two chemicals coming into this mixing tank. So the flow rates are what is available for me as to control. And these two chemicals have two concentrations, and they are mixed in this tank, and they have an exiting flow rate and an exiting concentration. So we start with the model of that system. So these equations are some mass balance. So this one is just saying it's some balance equations. So this is saying what is the volume, the rate of change of volume, what is this is the rate, I think this is the mass balance, and this final equation is actually an algebraic equation. So this whole thing about keeping this in, setting this option, is to write these equations without uh, muddling up those variables. Okay, so we get, so this object that you see here, later in the slide I'll show that all these objects are just first order ODEs of that system. So once I have this model, I'm just doing a brief analysis. So let me evaluate that. So I do a brief analysis. So I just give some disturbance to the flow rate of the second chemical, and I see that it takes a long time to settle, and this is what we want to improve. So the way we can improve this is this slow, the control design I'm using is pole placement, and the function is state feedback gains. And the slow response is because the eigenvalues or the poles are very sluggish. So I ended up choosing these two poles. Again, this is iterative. You choose some poles, and then you go ahead and try the performance of the system with that poles, and then you go from there and tweak them till you get something that's acceptable. So when I compute it, I ask for the data. So if I don't do that, I will get a pair of gains, but this is the controller gains itself, and I'll show how it comes into the overall picture. But with this, then we'll have to manually put everything together. So that's why I get this data object. So this data object is like the backbone or the linchpin of the whole design. So this data object knows what was the how to put the controller back with the plant, and this is what is going to enable us to automate the whole system. So from this object I can ask for a whole bunch of properties. So, okay, so the one I'm interested in here is to compute the closed loop system, and I'm setting merge false because I want to see the plant and the controller and not reduce it into one huge blob. Okay, so we have, so now a new feature that we have is we can also we have a property called block diagram. So we can so we can ask for, so once we compute that closed loop system, we can ask for the block diagram of that, and then we get a clearer picture of what this closed loop system is. It's a connections model. So this is the so this is more than just a pictorial representation. It will, you can actually mouse over it, and this will become important when we try to query the internal signals in this model, and that's one of the advantages of this connections model. So each of these subsystems have names, okay, and this will become important when we are trying to get these internal signals. And if you look at this connections model, here is just a blob. It says it has 2 inputs and 1 output. And you can actually come here and see that this are the first 2 inputs. This is the output. And for the internal signals, we just get what the count is. Okay, so once we have this closed loop system, then again, I'm going to compute the response of the system to that same disturbance. So these are the, so I give the same disturbance. And again, here I get a data object. So this object is like the linchpin of the design, and this object is the linchpin for the simulation. So what this data, if I don't have data, it just is going to return to me this output response. It's going to throw away all this information about the internal signals. But this data object has the information about all the internal signals. So I just do one simulation, and from that we can compute all those signals. So this also has a whole bunch of properties. Okay, and see, so one of them is output response, which is just the output of the system. And so I compute the output response, and I see that, you know, now I've actually improved. It doesn't take that much time to settle. Another signal that I would be interested in is in the control effort. Right, in this case, what is the, I'm limited in the amount of flow rate I can allow. So I would like to know what the flow rate is. So the way we get it is, so the control effort is, so maybe I can bring this block diagram down so it's easier to explain here. Okay, this control effort is this signal going here, and that is the output of this subsystem. So the way I get this internal signal is to ask for the subsystem response of that model, the comparator model, and that will tell me what those two trajectories are. Right. So okay. So this basic design, we had this configuration, okay, where we had the system with the controller. But typically when we implement it, this controller is implemented in a digital system like a microcontroller or some other device. And then we can simulate it upfront to see how it will behave, how the continuous time plant will behave with the discrete controller. And we get that by setting this option, sample data going to true. So now we have a closed loop system, but the difference is now it has these models inside. So this is what's called a sampler model. It takes a continuous time system and samples it to produce discrete. So this mimics what a microcontroller does. Okay, that's the, and it mimics that. And this one is the sampling of the states of the system. So this arrow is actually inside the system because it is the states, and the controller computes this and sends it out. When it sends it out to the plant, it holds that signal. So the sampler model and the holder models are what simulate model that behavior of a digital device. So I can take this sample data system and simulate it, and now we can compute its output response. Okay, and now we see that now, okay, I think I'm missing. Okay, so this response is actually a mixed continuous. This is actually continuous time coming from there, but the performance will not be as will not be the same as that of the continuous time system, because we have introduced some delay into the plant. And we can also compute what the control effort is. And when you see what the control effort is, we see that again. We see that again, it's a held signal, it's a digital signal, and it's piecewise constant. Okay, so now let's look at another control design. So this is the basic workflow. We have a model, then we have some analysis, design, and then we can see the closed loop and do the simulation. Again, these are the two uh, data objects, system model or controller data, and input output response data that are like the backbone of the design process. Okay, so, and you'll see that same thing repeated here again. Right. So in this case, I have a model of this system, which is a turret on top of this vehicle. And the objective here is to get this turret pointing in a certain direction. So the previous one was a regulator model, where regulator design, where I wanted to keep everything in equilibrium. And in this one, it's like a tracking. I want this to point in a certain direction. So I have this model of this turret, and I do a simulation. I find it's not that great. So the only change from the previous one is how I'm going to design it. Then the workflow will be like practically the same. So in this case, the input, I specify the input is the turret. In this model, the first is my feedback input. All the others are disturbances. So I say that's my feedback input, and I want to track the angle. The angle is the first output. So that's a design specification. And the control, last time I used pole placement. Here I'm using what's called an LQG regulator. So yeah, if you don't quite follow it, it really doesn't matter for this talk. But what it does basically is that it assumes that the disturbances are all white noise, zero mean processes, and we specify what are the covariances of that noise. It's basically going to compute a Kalman filter internally. And then for the cost, we want to minimize some performance metrics, and this is how we specify the cost. Those weights are, which I've increased, is really the weights for the error between the actual signal and my tracking signal, and this is the controller effort. But anyway, once I get past the design specification, I'm back to the same workflow. I have this data object, which has all the information about the configuration, and I get back this connections model, and now I see the block diagram, which is a little more involved than before. Okay, so we have this system here, and again, I can query. So now if you look at this closed loop system, you see that it has 6 inputs. We started with 4, and this is where this block diagram becomes really helpful, because earlier when we were doing the design, we have something like this, then we have to take a pen and paper to figure out like where these 6 inputs are coming from. So now we can see, okay, we have 6 inputs. Then we mouse over this, we see that, okay, these are the first 3 inputs going directly into the system. So those are the 3 disturbance signals. And see, this is number 4, which is the reference signal, which we can specify that the angle should be whatever we desire. And then the 2 other inputs are the noise that come through the sensors. And then we have the outputs. So what this controller is doing is it's measuring it's getting the output, it's getting corrupted with some sensor noise. It's coming into the estimator. The estimator is also being given the information about what is the input, what is the controller input going into the system. It has no control over the disturbances into the system. That disturbances is fed indirectly through the measurements. And the estimator estimates both what the position is and what the states of the system are. And this is the core controller, which is then computing the controller effort that needs to go in. Okay, so yeah, and then we do a simulation. I'm for simplicity, I'm assuming all this noise is just coming from a Gaussian distribution. And now I know what the inputs positions are. The first three are the noise, the process disturbances. The other two are the measurement disturbances. I've just set them all the same. And as before, I get this data object, which now has information about all the internal signals. And now I can compute the output response. And the first one is theta, which I see now has come to 5 degrees. And here now I'm again interested in the controller effort. So the controller effort is again the output of this comparator model. So this is the controller effort and that is the output of this comparator model. And so I get the controller effort too. Okay, so as before, I want to now simulate this with simulate this, imagining that I'm not going to do it in a continuous time, but my controller is actually going to be on a digital device. And so I get the closed loop system with sample data set to true, and this is the block diagram. Again, you see the sampler and it's the input, and this one is sampled, and there is a hold here. Okay, so I do the same simulation and I see the output response. Oh, okay, so you see the output response really deteriorated. And yeah, and this is because by default it takes a sampling period of 1, so it samples these at only 1 second. Yeah, so as I said, so sometimes it can reduce the performance, it can outright destabilize the system because we have introduced delays in the loop. So the way to rectify that is to tweak the sampling period to reduce it. So this is again a design parameter. So if you reduce the sampling period, you will get behavior close to the full continuous time simulation. But that means you consume more power, right? Your digital device, because it has to keep sampling so fast. But if you increase the sampling period, make it really large, then you will see this kind of behavior where the performance is reduced. So now when I increase the sampling period, I see I'm able to get back. And then I want to compute the controller effort as before. Then I'm just playing. So once I have the data object, I can compute all kinds of internal signals. So I'm asking for what the state response is. And from the estimator model, I'm getting its response. So that gives me the actual response of the system and the estimated response. And then I can compare the two. Yeah, here I'm just seeing how I can get various internal signals. Okay, and yeah, so again, from the subsystem, so each one of those, how we know what name to give there, you can mouse over and see what those names are. Okay, and so I'm getting this reference signal and the output of this estimator model, and that's what I'm comparing here. And I can see the actual and reference signals. Okay, so some of the things I want to point out from the previous slide is, so when we did that simulation, we had a sample data system with mixed discrete and continuous time systems. And we just gave it as a normal distribution. So what it's doing internally is, typically when we have a continuous time system, we'll give a continuous time signal. But now we allowed for a direct specification, like giving a normal distribution. What it is doing is that it's computing a whole bunch of random variates and it's then interpolating. So this is what is happening internally. It's creating a sequence and then doing an interpolation. Another faster way to do this is, if you just say you don't want it to sample at this, but suppose you want to sample at twice that, you can give the number of samples you want and then it will automatically compute. And then we do the same thing for discrete time systems. So for a discrete time, we do the counterpart for discrete time systems. So for discrete time systems, we can give a continuous time signal, and what it does is that it samples that signal. So this is what it does. It is sampling that. So then, okay, so we can also accept time series and temporal data. So this makes this function very general. So you can give any random process to it, which is essentially a temporal data, and get its response. Okay, so you can either give it as a temporal data, or you can give the random process directly and it will compute it. Okay. So this is me going quickly over what the sampler and hold models are. So you saw these models as subsystems in that closed loop system. So what a sampler model does is it takes a continuous time signal and converts it into a discrete time signal. This typically happens when signals are coming into a microcontroller. And we can just see what the response of that is. So this is the input signal, and this is what is the output of that. So typically it's a discrete time signal, but because we are doing the simulation, it's creating it as a piecewise continuous signal. Then you can also tweak that model. If you all this is gets filled in automatically when you are putting it into the closed loop system, because that object, the control design object, knows what the sampling period and the signal count and things like that are. But if you're working with just this model, you can customize this model and then simulate it for your purposes. And the holder model is the converse of that. It converts discrete time signals, that is the signals coming from a microcontroller, back into the continuous time world. So we have, so this is just the response of the default holder model. So this is the discrete input, and then this is the zero order hold approximation of that. So we can also change the order, we can increase the order, we can change the sampling period, and then compute its response. Okay, we can increase the order to anything we want, so we can make it 2, or but typically people use a zero order hold. So the order 2 uses the previous 3 signals to approximate the next interval. Okay, so another thing we added was the properties. So we have a state space model or any of these models, and then we can get a whole slew of properties from it. Earlier we could get them, but you had to actually go into the model and extract parts. But now, okay, these are all first class citizens. So if you have and you want to extract that matrix, you can ask for, okay, or you can ask for what the okay, so this basically allows you to extract this matrix and subsystems of this, and you can ask for a list of them. It just behaves like any other data object. And one property that is that can be useful is you can ask for what the equations are, because these are just representing equations, and you can get what the equations of that system are, or you can just ask for the state equations, output equations. And this is the same thing even for state space, or for the affine and nonlinear models. For the transfer function model, it's almost the same. So from here also you can get a bunch of properties. You can ask for what the underlying transfer function itself it gives you as an expression. You can ask for what the complex variables are, but this model is slightly different. It has these set of what are called equation properties. When you're asking, so the transfer function model is a frequency domain model, and when you ask for the equations, the ODEs, you have to convert it into time domain, and that's what these properties are. You can, so the transfer function also is a model in terms of an ODE or difference equation. So it will give you what the equations are, and for that it has to generate a lot of internal signals. So you don't have to like go and copy from them. You can ask that property what the input variables it used were, what were the equation variables, what were the output variables, the temporal variable. You can use all this to actually solve that transfer function model. And this is essentially what this response function is doing internally. It's getting all these properties. It's a triage function that gets all these properties, assembles the model, and sends it off to one of the solvers like dsolve or ndsolve or recurrence table. or rsolve, and you can see that we get the same result. Okay, the other thing we did was actually improve the appearance. So now we have, so this appearance is by default, it will choose something. So I have this model, it can fit everything here. So it gives you what we call a detailed model. So the model is slightly large. It cannot fit all these numbers on the screen. So this just shows you the structure. It's okay, you can mouse over that to see what those expressions are. And then if it's a little more bigger, we have this elide model where it shows you only the numbers at the boundary. And then if it's really large, we have, it just has an icon representation. Okay, so yeah, and then we can specify this explicitly in case you don't like the default behavior. So this is actually should be appearance detailed. Then you can explicitly ask for structured, elided, and iconized. And if you don't like the default, you can always give your custom icon and you can see it using that. And then, yeah, and okay, and then another thing we did was, now each of these objects has an attached cell where you can readily get this kind of information. You can see information about the model. You can see various simulation results. You can convert it into other models, okay, or you can convert it into one of these representations, one of these appearances. Okay. So to summarize my talk, what we have now is an automated and streamlined workflow for control design and deployment. The main function there is system model controller data, which allows you to actually get the complete controller configuration and whatever you need to facilitate the controller design. We have streamlined simulation, and the linchpin function there is input output response data, which simulates and stores all the internal signal information which you can query. And we also now have capabilities to compute the model properties and enhanced typesetting. So I'd encourage you to try this and let us know if you what you think about, and if you have any questions. So with that, I will conclude my talk, and if there are any questions, I will answer them. Oh, the question, yeah, all these features are for, some of them are in 14.1, but the vast majority, the question is this version 14.1? Yeah, some of them are in 14.1, but the vast majority are coming in 14.2. Okay, so I think if there are no more questions, we can wrap up. And I thank you all for attending.